The speaker of this session will be Julien Baglio from QuantumBasel and also the University of Basel. He will show some impressive results actually in the context of simulating NMR experiments in quite large scale on a computer. So please.
Yeah, thank you very much. So maybe a disclaimer after the previous talk, the result will not be as impressive, but that's not the goal. The goal here is to show why we need right now on current hardware methods to actually be able to extract meaningful data from what the quantum computer gives out. You will see that without careful messaging of your calculation, what you get out of current quantum computers is essentially garbage for this large scale system. So because I always do that now, in case you are bored or in case you are a bit sleepy, I start with the summary and then you can go away if you don't like, and then I'll continue. So as presented this morning just before, like NMR is an important tool, of course, for molecular structure. And let's say that it's to say that current techniques start to struggle for a number of spins a bit larger than 20, of course, depending on the structure of the molecules. Well, we've seen simulations around these which were impressively successful just minutes ago. But let's say that's the limit is currently above 20 spins, okay? And we also know that, as I've said, nowadays quantum computers are affected by noise. What I will present you is an advanced error suppression method for quantum Hamiltonian simulations, and I will present you a result with up to 34 spin. And we tried 2 quantum computers, IBM Quantum Computers and one on IonQ. I will also present you the characteristic of each of them. And our simulations, let's say the first success, we've been able to capture with the quantum algorithms the salient features of the spectra. So from that point of view, I'm quite happy. We see part of the substructure, but clearly not completely aligned with the classical simulation. So of course, there is room of improvement. But most importantly, you will see a clear reduction of the quantum noise. And that was our goal of this study. So we know the challenges are, one big challenge is the compute time, especially in trapped ion systems. And you will see why on these systems. And of course, all depends on the technique you use to simulate. And we use one trusted step, which is pretty harsh in approximation. That's well known. So the next steps is more detailed benchmark and trying to actually improve on the approximation side. I want to start with a problem statement, and I want to use your ITBQ framework that we adapted a little bit, especially for the problem at hand, which is a little bit tweaked from just solving NMR. So as I said, NMR spectroscopy is widely used, and we know the pain point, and we know that quantum may provide a way for quantum advantage, but specifically, we know that current computers are actually plagued with noise, and that's a relevant, let's say, I would say, practical challenge. That's why I rated that 4 stars. Our workflow really helped to reduce the quantum noise, so I rated also 4 stars. We were able to demonstrate in practice the efficiency in reducing the impact of noise when we compare to our classical benchmark, which is spinach there, but not perfectly, of course. So that's why I rated only, let's say, 3 stars. And let's say the way to quantum advantage, clearly not yet competitive with classical solutions, but it shows the path, especially with better quantum hardware. At least the pipeline here, I think, has proved its efficiency. That's why I rated 3 stars. So not too bad, actually. So previously, I will present stuff for high field quantum simulations in liquid NMR. And on the left-hand side, this is a result from last year from Artemi and Clément, my collaborators, for quantum simulation for ATP. With n equal 8 spin systems, with one throttle step on IBM Brisbane, which is now a computer which has been decommissioned, actually. And you can see clearly, so in red, that's the quantum simulations and reference spectrum in gray. And you see clearly the noise floor here, which is really due to the quantum noise. So this is something we want to reduce. On the right-hand side, it's a plot from this publication from last year as well. So it's trichlorobenzene with 3 spins in the system with 21 trotter stops, so pretty deep. On IBM PEP, also decommission doesn't exist. And you see 2 simulations on 2 different days. And you completely see the impact of the quantum noise, because not only it does not align perfectly with the reference in black, but also even if you compare the green line to the orange line, which are the same exact simulations from the mathematical point of view, but just on a quantum computer on 2 different days. So the specs changes, and you see that it changes drastically, and I mean, it's not aligned. So we want to improve on that. So again, my goal is to not to make the best quantum simulation with respect to the classical, but to improve the quantum such that it becomes reliable. For example, if I run on 2 different days, I get really let's say, identical results up to a threshold in error that I control. So that's the goal. So we selected 3 molecules which were identified for their hardness, and they are not announced because they were presented just before. So one which I call DFH, that's the defluorines molecule that Artemi was mentioning in the question. In B, that's the symmetric spectrum. So on the left-hand side, the DFH, that's n equals 16 spin for the fluorine spectrum. For the molecule in the center, the symmetric group, I will present to you results for both the proton spectrum and for the phosphorus spectrum. And on the right-hand side, that's the most, let's say, complicated from the quantum point of view molecule, because it has 34 spins in the phosphorus cluster.
Where did you get the Hamiltonian from with the spin Hamiltonian for this?
We use the chemical shifts and the spin-spin coupling, which were in spinach.
So is this cluster on the right in spinach also?
Yep.
Okay, interesting.
So yeah, true also. We didn't approach in the pipeline how to actually calculate this. We used that, but it's a good question. Yeah. And in the forthcoming paper, we will also present the spin system in the appendix. And actually, true, these maybe from the pure point of view of NMR, the one in the middle is the most complicated one, because that's the one in which the spin-spin coupling is the strongest. That's our analysis pipeline. So we start here on the top right with the molecular description. In the first thing, of course, the Hamiltonian definition. Then we do the time evolution, and this is where we will do some approximation, of course, first. We get a circuit, so we get quantum circuit with gates and operators. And then this becomes the input code for the central part that I will discuss a bit more, which is the error-suppression mitigation pipeline. All these steps I will present later on. Down at the very end, there is this measurement error mitigation, which happens classically post-processing the data. Everything before these, like black, which is a quantum computer, so all these 4 steps are actually before going on the quantum hardware. It's to like optimize the circuits. Then you get results. Then you can have the magnetization. You do the FFT, and then you have the spectrum. So that's the pipeline. So it first starts with the Hamiltonian simulation, how we define it. So things that were presented before, we start with Heisenberg Hamiltonian there. We go in the rotating frame, make things isotropic. So it means that the omegas and the j's are scalars, are not tensors at this stage. And the omega k here, it just contains the chemical shifts, and we have the spin coupling. Okay. We worked with pure states just to simplify our life. We also strong pulse, so we rotate all. We start from the zero. We apply a pi pulse and we in a transverse. And the Lee-Trotter formula. So the idea of the Lee-Trotter formula is you decompose your Hamiltonians in sub-Hamiltonians, and then you do the approximation of let's say, avoiding all the cross correlations between the subparts, making them small enough. And then you do this expansion there. And then, depending on the value of n trot, you are more or less approximate. Here we use 1, so it's the, let's say, the strongest approximation we can do. The thing is, if you want to go higher in the number of trotter steps, then you make the circuit deeper and deeper and deeper and deeper. Now there is the balance to pay. Okay, I want to be less approximate. I want to be a bit more accurate, but it makes my circuit much deeper. Now I go on the quantum computer, and there's noise, as I've just shown you before. So I'm accumulating noise. So what shall I do? So there is this balance to pay. And we started there with 1 trotter repetition just to see if we can already there correct the noise. Okay, I said I will deep dive in the error suppression. So we collaborated with Q-Control, and we used their tool, and it was tuned and optimized for our application. And we were actually the first use case on the IonQ computer, by the way. So it starts with the compiler passes sequences, already there to reduce the depth during the transpilation and to map the circuit and the native gate on the hardware. Already there, you'll see for IBM, this will have some impact. Then is the optimized layout selection, which means we really need to be sure that we take the qubit on our circuit to the good qubit on the actual quantum computer. Because, for example, on the IBM system, there is 156 qubits, but we only use up to 34 qubits. So you have to select the good 34 good qubits for your calculation. Step 3 is very important, is the dynamical decoupling steps. The idea there is to reduce as much as we can dephasing and ZZ crosstalks. And by doing so, you need to actually inject, so you add more gates, which seems a bit counterintuitive at this stage, but we add gates, so we add pulses, to actually counterbalance some other pulses which are already there, such that the 2 pulses together just cancel out. So that's actually very important. And the 4th step is AI-powered optimizer to optimize each 1 and 2 qubit gates, avoid parallel operation. For example, if I am on 1 qubit line, I have some gate operation, but I'm on 2nd qubit line just below. I want to make the operations slightly separated such that I avoid more and more this crosstalk between qubits, which is not needed. And the 5th one is the error mitigation, which is a classical post-processing, and it's using probabilistic error cancellation. So all in all, yeah?
So you're doing essentially anti-layering, but that introduces a lot of idle time.
Yes,
Okay.
it does introduce idle time. Exactly, that's part of the gates, so to say, which are added, actually. But yes, it does, precisely to display some operations that there is, I'm avoiding, for example, this crosstalk. Indeed, it does.
So you found it easier to treat the idle time than the crosstalk.
That's the 2 systems we are looking at. And on the left-hand side is the IBM Aachen. On the right-hand side, the Forte Enterprise IonQ systems. So each of these systems has pros and cons. So the pros of IBM are well known. It's fast operations, much faster operation than on IonQ. And that you can see easily with the readout time, 2 qubit gate time, 1 qubit gate time. Here it's in microseconds. So you see it's always below 1. And then suddenly this column here is for IonQ, it's like 63, 650, 250. So it's really much slower. On the other hand, IonQ has all-to-all connectivity. And this is very important in terms of circuit depth. And you'll see the impact in the results I'll present. The error rates are pretty much comparable. There is one also striking important difference. On IonQ, at the moment, the technology they used, all operations are sequential. While on IBM, I can do parallel operation. So, one results. Improvement in FID. So here I'm just showing you on the left-hand side the first 800 time points for the hydrogen FID of the symmetric molecule. And on the right-hand side, I'm just zooming over the first 240 points. And you can see immediately by comparing the dashed black line, which is the ideal case that we could simulate for these few points on a noiseless simulator, against what comes out directly from the system in red. And then in blue is the error suppressed and corrected and mitigated. And you see that if I were to just look at the red plot, it's essentially garbage at what I get. I'm really far away from what I should get if I had an ideal quantum computer. While with the error suppression and mitigation pipeline that I've just presented you before, we will cover most of the actual signal. So if you compare in terms of mean square error between the baseline, which is the black, against the result in the quantum computer, there is like on the first 240 points, a 22 times improvement in MSE. Here on the overall is like 11. So it's a sizable improvement. So already there, I could stop and say it works, which is pretty good. In depth reduction, so we really had a consistent depth reduction over all spectra for all molecules when I look at the 2-qubit circuit depth. And that's the one I'm interested in the most because that's the most noisy one. And 2-qubit gates are the most noisy gates in the circuit. And actually what happens there, and it comes back to your point actually, I am training off 2-qubit gates with 1-qubit gates, but in such a way that down the road, even if I have more 1-qubit gates than in the error-suppressed pipeline than in the row pipeline, I have reduced so much my 2-qubit gates that the overall effect is positive and the error are reduced. And you can see it there, like the 2-qubit gates is always lower when I have my error suppression pipeline, and the 1-qubit gates sometimes are lower, but sometimes they're always bigger. Sometimes not too much, sometimes significantly. So that's also one counterintuitive point maybe. For the spectra, this is what we get. So first thing first, the noise floor is significantly reduced. If I recall you the very first plot I presented you, which was very noisy for a smaller molecule. Here we start with 16 spin, 22, 22. Here for the P spectrum, we can start to see it. Of course, now we see it even more for the 34 spins. But what is important is in all 4 cases, the position of the peaks is there. Now, of course, if we zoom in, and that was not the point, but still, I present you, we don't capture the substructure, but we see the beginning of it. Clearly, we don't have the correct width and so on and so forth, but we see it. So there is some hints of substructure already there with a very rough approximation. It's only 1 cluster steps. And here we are in a deep regime for quantum computing. It's really deep regime. So pretty nice results. Now, what happens on IonQ? Slower operations. So we also analyzed the number of shots we wanted. Here we only use 700 shots. And well, the results are pretty consistent, let's say. Again, not very good on capturing the actual structure, but we see some substructure, and the main peaks are there. Also, some spikes that we see on the IBM output seems to be avoided, especially in the FID.
Wait, can you just?
Yeah.
We have the red line that is on the.
So the let's say the dark line is the IonQ line, and the dashed line is the one from IBM there.
And how should it be? The ideal?
When
we look at
the ideal one, maybe look in the, okay, the zoom one is, the ideal one should be in blue, let's say.
Yes.
And this is the dashed line is IBM, and the solid line is IonQ. So
you get these 2 satellite peaks on the left and right, and the middle is off. So
the middle is off.
That's interesting.
Yeah.
Okay, thanks.
Indeed. So of course, again, room to improvement, but let's say we are on a good way.
I mean, it could also be a function from the fact that you use only 1 drop.
Yeah. That's what I mean. It's pretty much because of that. It's pretty much this plus the spectral also resolution. You mean do the noiseless simulation of the quantum system? Well, yeah, this is the baseline of, for example, this plot. This plot, the black line is it's really the best you could get out of a quantum computer with no error and with our let's say, approximation, indeed. So I'm pretty much done, I think. I just wanted to tell you that we have access to 3 quantum computers if you want. And I just come back to the executive summary. And if you have questions, there's 1 minute left for questions. So I let the floor to you. Thank you.